We're going to wrap up our introduction to binary trees with modification of binary search trees, insertion and deletion. So the key point to any modification of a binary search tree is we must maintain both the fact that it's a binary tree, which isn't hard because your data structure won't let you do otherwise, but more importantly that we maintain the binary search tree property, the ordering of the keys, such that if y is in x, the left subtree of x, then y's key is less than x's key, and any y in the right subtree of x must have a greater key than x. So this is what we have to think about in doing the modification. It turns out to be that it's very simple with insertion, because we can always insert at a leaf position, just basically searching for the node and then searching for the key and not finding it and then putting it where we would have expected to find it. But deletion, we might be deleting an internal node, and so various rearrangements are needed to do that. Now insertion is quite straightforward. All we have to do is look for the position we expect the key to be in the tree, and when we don't find it, we just put it there. So let's suppose we want to add a node D. We assume that the node has already been constructed and the key field has been initialized and its children are set to nil. So what you do is you go into the tree, do the search here. D is less than H, D is greater than B, D is less than G, D is less than E, D is greater than C. But when we go to the right child of C, using the search procedure, there's nothing there, so we know that we can put it there. So basically we just need to keep track of, as we search down, what was the node we just came from and where are we at now, so that when we fall off the tree and a variable becomes nil, we've kept track of the parent we just came from, and then it's very easy to just add that node to the tree as the child down the direction that we just went. Let's look at another example. We're going to insert the node J, so H greater, less than. So less than means search the left subtree. The left subtree is nil, and so then we add the J here. And here's the code for insertion. Y is playing the role of the trailing, and X is playing the role of the leading pointer in the search. As I mentioned, when we fall off the tree, we need to have somebody kept track of where we fell off of. So Y initially starts to nil, and X starts at the root. And this is just a version of the search procedure where we step down, we record where we were with X, and we do the comparison, and then we go either left or right depending on where we were. So, for example, when we were searching for the position to put D in, at some point Y was this, X was that, and then Y was assigned to be where X is, and then X was revised to be down here, but at that point it wasn't there yet, so the X became nil. So X became nil, and then we drop down here. And then you just take the node you're trying to insert, which is Z is this node here, and you set it to be the last node that you visited before you found the position. And you also have to deal with the special case that the tree is empty, so we just make the root be the node we're inserting, and this is the code that actually puts it on the correct side of the of Y. So I leave it to you to run through some examples with this code to see that this code works, and let's now consider the complexity of the code. Well, we know the complexity is going to be the same as tree search because we have to search down the tree, potentially order of H. We have some constant operations here, constant operations here. These are all constants. This is just testing if statements and doing constant operations. So it's dominated by the search, which is the same as for the tree search. So insertion is going to be big O of H, where H is the height of the tree. Deletion is more complex because the node to be deleted may have children. It may not have children, but it may also have children. So we have to think of this in terms of different cases. So let's look at the first case where Z has no children. This is simple. Just remove it. So an example would be if we're deleting F. Of course, we would have to do a search first to find it, and we would know it has no children, and so we would just delete it by, of course, modifying e.write to be nil. Now I'm going to need that node later, so we'll bring it back. But another example would be if you're deleting a left child, J. Same thing. You would just set k.left to be nil. Now let's look at the next case where node Z has one child, C. We can replace Z with C, dragging up C's subtree. So let's look at an example of that. Well, let's say we're going to delete G. Okay, G has one child. We would remove the node G, drag this whole subtree up to there, attaching it to be the right child of B. So essentially we replace B.write with E, and that splices G out of the tree. Another example of that is I. If I'm deleting I, then I've got to drag up K to be the right child of H. The third case, of course, is where Z has two children. And this is rather more involved. The first thing we're going to have to do is find Z's successor, Y. And once we've found that, we want to basically replace Z by Y in the tree. Okay, but this itself is rather involved. Let's look at some examples. Well, the simple examples are like with E. We're going to delete E, and we find E's successor. E's successor is F. And by the way, the fact that Z has two children makes it easy to find the successor, because remember, the successor procedure had to deal with two cases, one where Z had two children and one where it didn't. And where it didn't was where we had to do the weird thing of climbing the left up the parent links up to the left until we couldn't go left anymore and then going right. But here we don't have to do that because Z has a right subtree, and we know that the successor to Z must be in that right subtree. And also we have a procedure for finding it, which is the minimum of the right subtree, because those are all the nodes that are larger than the keys are larger than the key of the one we're looking at, Z. And so we just find the minimum of those that are larger, and then that will be the successor. So it's pretty easy to find this successor here. Now in this case, like we have here with E, there's no children involved, and so we can just pull that up. We can just replace E with F in the tree, or replace Z by Y in the tree. Here E is playing the role of Z, and F is playing the role of Y. Another example would be with K, where if K is a node Z to be deleted, and then the successor is in the left subtree, so that's the successor. So all we have to do is just drag that up and replace it. Obviously these operations will involve changes of pointers. Now you might think, well, why not just set Z.key to be F? In other words, copy the data from that node to that node. The problem with that is that if some other program is maintaining pointers into positions in the tree, remember there's a position abstraction, or these could be private methods that are used, shared with other methods are using the same data structure, and so they might be pointing at something in here, and then we suddenly copy the data up there and we think we're pointing at the node with E in it, but we're really pointing at the node with F in it. So rather than just copy the data up, we're actually going to have to splice things when we implement this, to splice out, G no longer points to E, G points to F, and now F points to whatever E's child was, and so on. So there's a splicing operation involved. So we just replace Z by Y and we're done. Of course, that replacement involving all the stuff I just discussed. But otherwise, we have the situation where the successor Z is somewhere in Z's right subtree. And again, we know it has no left child, so we don't have to worry about what we do with that left child. And so the otherwise procedure will have 3 steps. So it's in the right subtree, but it's not a child of Z. So what we're going to do then is replace Y with its own right child, and then the rest of Z's right subtree becomes Y's new right subtree. And then Z's left subtree will become Y's new left subtree. Okay, let's look at an example of this. So the node in this tree that fits this case is if we wanted to delete B. So let's say B is node Z, and then we're going to search for B's successor. So we go to its right subtree, and we keep going left until we can't go left anymore. And that's going to be Y, the successor for Z. And so Y is in Z's right subtree, but it's not Z's direct child. So we're going to, ultimately, we're going to put C in this position up here. But before we can do that, we have to do these other things. So we're going to replace Y with its right child. Here we have a right child, D. There could be more of a tree down there, actually. So what that means, to replace Y with its right child, is Y's parent now points to what was Y's child. So we do that. And again, technically, this link is still in there right now. But now the rest of Z's right subtree becomes Y's right subtree. So that's where this link gets erased. This stuff becomes Y's right subtree. So it would be a link like that. But rather than draw it that messy way, I'm going to go ahead and move C up to where it's going to end up so you can see what's happening. And put C up there. Okay, so the operation we've just done, rest of Z's right subtree becomes Y's right subtree. We've just done that. Now technically, again, B is still pointing to that. Probably it doesn't matter, it'll be garbage collected, but if there's a reason you think it matters, you could set it to nil. Now Z's left subtree becomes Y's left subtree. So here's Z's left subtree, and so we set Y.left to be what Z.left was. Oh, there's one thing that's not written out here, which is, of course, the parent has to now point to C instead of B. So let's complete that link there. Up until that point, this was technically still pointing over here. So you can see now that we've successfully gotten B out of there and put C in the right position. And we've done it by keeping C in the same container. We didn't copy data. So if there was some external client or using a position abstraction or something in the class pointing to that node, then it would still be pointing to the same node that contains C. Incorrect versions of deletion will not do that. They'll move keys around to make the code simpler, but incorrect. And we have sustained the binary search tree property that C is less than H, and G is greater than C, A is less than A, and all these things here are greater than C. So the ordering is preserved. That's the really important thing. Okay, so those are the conceptual cases and examples, and this all now plays out differently in the actual code. So we're going to go look at the code briefly. So here's the code for deletion. This deletion code assumes that nodes have pointers back to their parents, like u.p is going from u to its parent. And as I mentioned in the examples, when we replace a node, like when B was replaced with one of its children, C, we had to update the parent of B to point to B. And it matters whether B was the parent's left child or right child, so you have to test for that. So there's a lot of code that you're going to have to do repeatedly in several situations. It's kind of picky stuff. And that's all wrapped up in this transplant thing. And so what transplant does is it essentially replaces U with V from the parent's point of view. It does not handle the child links of U and V. It's not going to update them. That's going to be done by the main procedure that's using transplant. It's just going to take care of all the issues like, well, what if we're actually putting a node at the root, so that's a special case. Otherwise, if the node we're replacing was the left child of the parent, then make the new node be the new left child of the parent. Else, if the node we're replacing is the right child of the parent, make the new node be the right child of the parent. Here's where we have the parent pointers themselves updated. Make V point up to its new parent. Okay, so all that takes care of the parent stuff. We no longer have to worry about it. And now let's look at the tree deletion procedure. So the first case is here, where there is no left child. This code breaks things down into 4 cases we're going to see here. And we just went through a conceptual overview that had 3 cases. lines 1 and 2 handle the first case of the conceptual example where there's no children, and it handles half of the second case where there's one child. This part's going to handle the other half of the second case where there's one child on the left side, because we fell through here. So if there's no left child, then all we have to do is replace the node with its right child. So like C has no left child, we just got to transplant D to be in C's position, and since there's no other children involved to be concerned with, all we have to do is call transplant. So transplant Z, the node we're replacing, with Z.right, its right child, and we're done. The second case, there is a left child, but there's no right child. So an example of that would be up here, G, where we have a left child but no right child. And again, we can just do the transplant operation. We can take G is now playing the role of Z, and we can now transplant Z.left, which is E, to move it up into this position, and nothing else has to be changed. So now we've dealt with the cases where there's only one child, so the rest of this code here will be 2 children in this else. So remember, when there's 2 children, the first thing we did is we found the successor of the node to be deleted. And because there's 2 children, we know there's a right subtree, so we can just go into the right subtree that has keys greater than Z's key, and we can find the minimum of that tree, and that has to be the successor. So that's pretty straightforward. And now we can ask, is the successor we found, is it the child of the node we're deleting? Of course, the code actually tests for it not being the child first, because it's going to do some other stuff and then reduce it to a condition where it is the child. And so this code will apply in both cases. So assume that once we got to this point, the successor is a child, whether it's been up here making it the child or not. This was the third example we looked at above. So the example here in the tree would be, for example, E. So if E is the node to be deleted, Z, and we go to the right subtree and we find the successor, that's going to be node Y, and the successor is a child. So this test fails. We drop straight down to here, and so we just transplant the successor to replace the node we're deleting, just like before. But unlike these previous cases, we can't just plop that up there from the point of view of the parent, make G point to F, because we would have lost track of this the left subtree. So we have to say Y.left is Z's.left. So then F here on the left will now be pointing to C, and we got to make Y.left at P be Y. In other words, make C point back up to F. Okay, so the last case is where the successor is not the child. So this involves multiple step operation on the trees, and there's some nice diagrams in my web notes that come from the textbook, so you may want to, you should read them. So an example of this, as we saw before, is with B. Let's say we want to delete B, which is going to play the role of Z, and we run the tree minimum on the right tree, and we find the successor. C is going to play the role of Y here. And we're going to say if Y parent not equals Z, no, Y parent is E, we're going to run this. So first we're going to transplant Y.right. So we're going to transplant, actually C is going to play the role of U in the transplant code, and D will be V in the transplant code. So we're transplanting D up to where C is. And so let's go up here. It's not nil. U's parent is U's parent's left. In other words, U is a left child. So we're going to set U parent's left is V. And by the way, I've only got one line here, but there's really pointers in both directions. Maybe I should start drawing them with arrowheads here. So this makes U parent left point to V. It points down there now. And if V is not nil, V's parent becomes U's parent. So there was a parent pointer sitting here, and so now V is going to point up to there. Okay, transplant returns. Now we're going to say Y.right is Z.right. So this is where we now take Y.right, and I'll go ahead and erase that. It's going to be set later. I just want to get this out of the way. Okay, y.right becomes z.right. All right, so now that's going to point down there. And y.right, that parent, becomes y. Again, there's really pointers in two directions here. So what that line does is erases that line and makes it go to this one here. And now we drop out of that if and we call the rest of this here. We're going to transplant z, y, replace z with y. We've already run through this before. Essentially it says the parent figures out I'm no longer pointing to B, I'm pointing to C here, and it works in both directions. You know, there'll be right here will be where the parent points down to C, and then right here will be where the C nodes points up to the correct parent. Essentially we now have made this correct in both directions. And then y.left is z.left, so we got to take z's subtree and put it in there, and z.left's parent is y, so this is z.left's parent is y, so that's completing that part there. So now we have successfully spliced in C into the structure of the tree, same modification I made before to this tree, and we've done so while retaining what used to be C's right subtree is also part of the tree. But I'm going to go ahead and just complete the modification. Okay, so that completes the discussion of how the deletion works. But before we leave deletion, let's make a note on its complexity, time complexity. Okay, transplant. Everything else in here is just constant operations inside if tests. No looping or dependency on n involved. Tree delete. These are all constant operations, and all this down here is constant operations. The one thing that would not be constant is the tree minimum will depend on how far down the tree it has to go to find the successor that we're looking for. And we already know that the tree to the minimum is big O of the height of the tree. So that's going to be the one thing that grows as n increases. It will dominate the complexity of deletion. So that leaves us with the question of what h is. That concludes our discussion of modifying binary search trees. Next, we will have a brief screencast on analyzing the performance of binary search trees.